Hello, this is Professor Kuehn. Welcome back to our discussion of Einstein's theory of relativity. I think this will be my last lecture on A Student's Guide to the Grade Physics Texts, Chapter 30, which is on the absolute speed of light. We've been talking about both time dilation and length contraction. That is that time intervals between events and the lengths of objects are different when measured by observers who are in motion relative to one another. This is a consequence of accepting the constancy of the speed of light. Now what I'd like to do is work through an example of length contraction and time dilation. This is a bit more involved example, but if you grasp this, then I think you're doing quite well. Here's the idea. Let's suppose that there's a spaceship that is going to be traveling at a uniform speed. That should make you realize that we're talking about an inertial reference frame. A spaceship, as I mentioned, travels at a uniform speed or uniform velocity between Earth and nearby Alpha-Centauri. So Alpha-Centauri is a star, one of the ones nearest to the Earth. And let's suppose that this spaceship is traveling at 95% the speed of light. Some of these numbers are going to sound a little bit outlandish, and it's admittedly a bit contrived in order to make the problem more interesting. So the ship travels at 0.95 c, or 95% of the speed of light, compared to Earth, or with respect to both the Earth and Alpha-Centauri. So the picture you should have in your mind is something like this. You've got Earth over here, and you've got Alpha-Centauri, a star, over here, and these reside in a particular reference frame. They are at rest relative to one another. And then you've got this spaceship that is traveling from Earth to Alpha-Centauri at some high speed compared to an observer who might be standing on Earth. So if there's a person over here and maybe another person who's floating over here near Alpha-Centauri. So these are the two inertial reference frames we're talking about. The first inertial reference frame would be occupied by the Earth and Alpha-Centauri. They're at rest compared to one another. They see the ship moving at a speed of 0.95 c compared to them. The other inertial reference frame would be the astronaut who's on the ship, who sees the Earth and Alpha-Centauri rushing past in the opposite direction, and to him, those two objects are traveling at 95% of the speed of light in the other direction. So once again, they agree on the relative speed, they just disagree about who's in motion. Okay, so let's make a couple of other comments here. So that's the picture you should be having in your mind. Let's talk about, first of all, the distance between Earth and Alpha-Centauri as measured by these observers who are at rest relative to the Earth. So the distance between Earth and Alpha-Centauri as measured by the Earth observer, or Earth-bound observer, is 4.3 light years. If you're not familiar with a light year, it's a measure of distance. It's basically how far light will travel in 1 year. So if you shoot a light beam from Earth to Alpha-Centauri, it would take 4.3 years for the light to get there, as measured by the people on the Earth and on Alpha-Centauri. Okay? Sometimes that distance would be written as 4.3 years times c, the speed of light, because the speed of light is measured in meters per second, or distance over time. You multiply that by time and you get a distance. Okay, we'll come back to that again in a moment. Now here's the question I want to ask. How much does an Earth-bound observer age, and how much does the spaceship-bound observer age during the trip? So how much do, first of all, an Earth-bound observer, or the Earth-bound observer, and two, the spaceship-bound astronaut, the guy riding on the ship, age during this trip from Earth to Alpha-Centauri? That is the question. And do they age by the same amount? The answer is going to be no. I'll just give you a heads up. Now we have to think carefully about what we mean by this trip. Okay, so let's clarify something right away. This is going to be helpful. When we say this trip, we basically mean the time between two events. Those events are when the spaceship leaves the Earth and when it arrives at Alpha-Centauri. So let's just clarify that. So we have event 1 would be the spaceship leaves Earth. Okay, that's event 1. And event 2 would be the spaceship arrives at Alpha Centauri. At Alpha Centauri. Okay, so when we ask the length of the trip or the time interval of the trip, we're asking about the time interval between these two events. Now, there's something that might be worrying you, or that maybe should worry you as we continue this discussion. When the spaceship leaves the Earth, of course, if it's first sitting at rest compared to the Earth, it's got to accelerate up to some speed of 95% the speed of light. And so for that time interval while it's accelerating, that astronaut is not in an inertial reference frame. And so a lot of what we've been talking about becomes a bit more complicated. Not that it can't be solved, it's just a more complicated analysis. And so what I'd like to do is I'd like to ask you to suspend your judgment about this for a moment and just allow that this spaceship is immediately going at a speed of 95% the speed of light. Or if you like, maybe think about the time interval. If this ship is just flying past at a constant rate, event 1 would be when the ship passes the Earth, and event 2 would be when it passes Alpha Centauri. And in that sense, that astronaut on the ship is always in an inertial reference frame, and we're simply asking the time interval between when he passes Earth and passes Alpha Centauri. Okay? So with that caveat, let's continue our discussion. Okay? Now, the question that we should be asking right away is which of these observers, we're going to need to talk about lengths and times. So we're going to have to be using these time dilation and length contraction formulas. So let me just write these down right away. This is the length contraction formula, or relativistic length contraction formula. And the time dilation formula, delta t equals gamma times delta t naught. This would be the time dilation formula. Okay, so these relate the lengths as measured by the two observers. These relate the time intervals as measured by the two observers. Okay, and maybe I should say one other thing just to clarify something. If you're talking about the relationship between speed, distance, and time for a single observer, you can use the standard formulas for velocity. So for example, if something is moving at a certain velocity according to one of these observers, that would be the length or the distance according to one of the observers, according to an observer, divided by the time according to the same observer. So there's no gamma that works into this formula. If you want to know how fast you're moving, you need to know the length through which you're moving as measured by yourself and the time interval of your motion as measured by yourself. So there's no gamma that appears in that formula. The gammas appear when connecting the lengths as measured by different observers and connecting the times as measured by different observers. Okay, so it's probably worthwhile just clarifying that at this point. Now, let me point out another thing. Notice that the earthbound observer is the one who measures the proper length or the distance between Earth and Alpha Centauri. So the earthbound observer measures what we would call L naught. That is the proper distance, the proper length or distance between Earth and Alpha Centauri. Why is this? Well, think back to our definition of proper length. The proper length is the length of an object that, in that case, it would be the length between Earth and Alpha Centauri as measured by an observer who is at rest with respect to that object you're trying to measure the length of. Okay, so you might think about a long ruler placed between those two, and that length is being measured with respect to the Earth, which is stationary, and Alpha Centauri, which is stationary. Okay, so the earthbound observer is measuring L naught. What about who is measuring the proper time between these two events? So notice that the astronaut aboard the ship, is measuring the proper time, delta t naught, proper time between the events that define the trip, the events 1 and 2. How do we know that? Well, think about this for a moment. What are the two events? They're when the astronaut leaves Earth and when the astronaut arrives at Alpha Centauri. The people on the Earth and Alpha Centauri would say those two events happen at different locations. Whereas the person on the spaceship, he sees Earth pass, that's a certain place in his coordinate system, that's one event, and then the Earth flies off, and then Alpha Centauri comes and arrives at him, that's a second event. Those are both happening at the exact same location in his coordinate system, so the astronaut aboard the ship would be measuring delta t naught. Okay, so once again, we have this situation where one set of observers is measuring L naught, and the other observer or set of observers is measuring delta t naught. Okay, so having put behind us those preliminary comments, let's write down some formulas. First of all, what is the proper length, L naught, between Earth and Alpha Centauri? Well, we were told that it's 4.3 light years. So another way of saying that is 4.3 years times the speed of light. we could write the speed of light in meters per year and then multiply by 4.3 years, and that would be the proper length or the distance between Earth and Alpha Centauri. So why don't I just write that right here, because this picture really captures the perspective of the people on Earth and Alpha Centauri. They're measuring the proper length. Okay? Now, what would be the time interval between when the astronaut leaves the Earth and arrives at Alpha Centauri from the perspective of the people on the Earth? Well, remember, they're not measuring delta t naught, they're measuring delta t. So the time interval would be equal to the proper length divided by the speed of the ship. This is really using this idea right here, that the velocity is a length over the time as measured by the same set of observers. Okay, so what is the proper length? It's 4.3 years times the speed of light, divided by the speed of the ship, which is 0.95 c, 95% of the speed of light. I left the c's in here so that I could cancel them out like this. So you take 4.3 years divided by 0.95, and so it would be 4.5 years. That is the time of the trip as observed by people who are standing on the Earth or Alpha Centauri. That is, they will have aged 4.5 years during this trip. So the Earth-bound and Alpha Centauri-bound observers will age 4.5 years between when the astronaut leaves the Earth and when the astronaut arrives at Alpha Centauri. Now the question that remains is how much does the astronaut on the ship age? Well, remember, he is measuring delta t naught, the proper time interval between the events that define the trip, and we can obtain delta t naught from delta t using this time dilation formula up here. So we can solve for delta t naught. It would be delta t divided by gamma. I'm rearranging the time dilation formula. And we just found delta t was 4.5 years. And now we need to plug in gamma. I'll write that down here. It would be whoops, I guess gamma is in the denominator. So let me go back a moment. So gamma is 1 over 1 minus v squared over c squared. Okay, and we can plug in our numbers. 4.5 years times 1 minus 0.95 c squared over c squared. And I did these calculations previously, so we end up getting 1.4 years. Okay? In other words, what's happening here is whereas the people on Earth and Alpha Centauri will age 4.5 years, the astronaut himself or herself who's on the ship will only have aged 1.4 years. That is because time travels or time elapses differently for these observers who are in motion relative to one another. So the astronaut sees 1.4 years elapse during the trip. The Earthbound observer sees 4.5 years elapse. Now, let me say one other thing before we move on. What is the distance that is traveled by these observers? So let me erase something here. If I go over here and do some erasing, hope you don't mind if I erase at the top. Well, I could stop and go on to another lecture, but I'll finish this one off, okay? So what is the distance traveled? So this maybe is question 2, call this question 1. What is the distance traveled according to both sets of observers? Okay, well, we already said that according to the Earthbound observer, the distance that was traveled was 4.3 light years. So according to the Earthbound observer, the distance was L naught, which was, like we said, 4.3 light years. 4.3 light years. Is that the same distance that this astronaut himself sees? Well, the answer is no. He sees the distance to be L naught over gamma. And so if you plug in 4.3 years times c and divide by our gamma factor, which we had just computed for the other one, you would see that he sees a distance of 1.3 light years. Okay, notice that the observer on the spaceship ages 1.4 years, and he sees that the distance is 1.3 light years. So the two observers, they disagree on the distance of the trip, and they disagree on the time intervals of the trip, but they agree on the relative speed v, and they also agree on the speed of light c. Okay, I'm going to stop there, and next time I think we're going to go on to the next phenomenon we'd like to discuss, and that is relativistic mass increase.